Hello everyone, I am Samyukta and I am here to kickstart the presentation of our IoT project on home automation, a smarter way to monitor and manage your home. Today, I'll be presenting about the foundational concepts of C and C++ programming, what they are, why we use them, and how they tie together in building robust applications. My focus will be on the core ideas that we covered in class: syntax, data types, control flow, memory, and object oriented programming. Now, let's begin with C. C is often described as a middle level language. It offers the efficiency and control of a low level programming with the readability and foundational courses of high level languages. Because of this, it's widely used for system programming, embedded systems, and situations where you need precise control over hardware and memory. In our coursework, we learned the basics of C, how programs are structured, how statements end in semicolons, how code blocks are defined with braces, and how C treats data in a granular way. In C, understanding how numbers are represented is crucial. We covered various number systems like decimal, binary, octal, and hexadecimal. We learned that data is stored in bits and bytes, that a word might be 2, 4, or more byte depending on the machine. We also learned about signed and unsigned data and how 2's complement is used for representing negative numbers. These foundational matter when you are dealing with the low level data manipulation, bit shifts, or memory layout. Next, we looked at the basic data types in C: int, char, float, and double. These helps us to represent whole numbers, characters, decimal numbers, and higher precision numbers. Type modifiers such as short, long, signed, and unsigned allow us to adjust the size or meaning of these data types. For instance, an unsigned int cannot hold negative values but gives a larger positive range. We also discussed overflow when a value exceeds the maximum for its type, and underflow when it falls below the minimum, which can lead to bugs if not handled carefully. Next, let me move on to operators. Operators in C are our tools for performing computation, logic, and memory manipulation. We covered relational operators like less than, greater than, equal to, not equal to, etc. Logical operators like and, or, not equal to, and assignment operators like equal to, plus and equal to, minus equal to, and so forth. Bitwise operators like ampersand or less than, negation, greater than, and other useful operators like size of, which returns storage size, and the ternary operator question mark with semicolon, which lets us write compact if style logic. Mastering operators helps you write expressive and efficient C code. Now, let's see about the control flow and input and output. Control flow and input and output are what let your program make decisions, repeat tasks, and interact with the user. In C, we used printf for output and scanf for input. These are straightforward but essential. For control, we used if, else, switch statements to branch code based on conditions. We relied on loops like for loop, while loop, do while loop to repeat operations. And like jump statements, which are break and continue, helps us fine tune our loop behavior. These constructs are universal in programming, and mastering them sets a strong base. Now, let's look upon the arrays, functions, and pointers. Moving on, these are the key to writing modular, efficient code in C. Arrays lets us store many values of the same data type in contiguous memory. Functions enable us to write reusable blocks of code, taking input arguments and returning results. We explored argument passing by value, copying data, and by reference, passing address, which is especially important when pointers come into play. Pointers allows us to store addresses of variables, enabling dynamic memory use, efficient arrays, linked structures, and more. We learned about pointer issues such as wild pointer that are uninitialized and null pointers pointing to nothing, and how the constant keyword can help protect data from unintended changes. Now let's go back to memory and storage. Memory and storage discussions helped us understand what happens under the hood. Indianness, like Little Indian, Big Indian, explains how bytes are ordered in memory. We looked at different memory segments, like the stack for local variables and function calls, the heap for dynamic allocation, the data segment for global or static variables, and the code or text segment for executable instructions and constants. Storage classes like auto, register, static, extern influence variable scope, lifetime, and linkage. Knowing where data resides and how long it takes lives is crucial in systems programming and embedded projects. Now let's talk about the last concept of C programming: strings and preprocessor. Strings in C are sequences of characters ending with a null terminator. We learned to declare and manipulate strings using character arrays and string pointers, understanding that some are modifiable while string literals are read only. We covered preprocessor directives, which control how programs are compiled. Example: hash include to add header files, hash define to create constants or macros, and head guards to prevent multiple inclusions of the same file. These tools make our programs clearer, reusable, and easier to maintain. Now, let's conclude with the basics of C and move on to the most functional and highly oriented C++. Once we had a solid foundation in C, we transitioned to C++, which builds on C but adds object oriented programming (OOP) features. OOP lets us model real world entities as objects with state and behavior, improving modularity, reusability, and maintainability of code. We learned about classes and objects, access specifiers such as private, public, and protected, constructors, which initialize objects, and destructors, which will clean up. This tool helps us design more complex systems in a structured way. Now, let's look at the most and prominent pillars of OOP. We have covered four pillars of OOP. First being the encapsulation, combining data and methods within a class. Second being abstraction, hiding internal details from the user. Third, inheritance, reusing code from a parent class. We studied types of single, multi-level, multiple, hierarchical, and hybrid. The fourth, the most important, polymorphism. Now, let's look into polymorphism in a little detail. Polymorphism. This allows functions or operators to behave differently depending on context. Compile time via overloading and runtime via overriding. Together, these concepts let us craft flexible and scalable software. In this course of class, we didn't just learn these concepts in isolation, we applied them in our project, Automated Home project. We used C for low level device control and C for structuring our modules using classes, inheritance, and polymorphism. This combination allowed our system to be more modular, efficient, and extensible, a real world demonstration to the theory we learned.
Hello all, I'm Esritika and today I'll be presenting about the Internet of Things or IoT. IoT is a network of physical objects like sensors, appliances or vehicles connected to the internet to collect and share data. It helps automate tasks and make real-time decisions without human intervention. IoT systems are typically built with four layers: the device layer for sensing and control, the network layer for communication, the cloud layer for storage and processing, and finally the application layer that interacts with the user. We see IoT everywhere today, from smart homes and wearable health devices to industrial automation and agriculture systems. The goal of IoT is simple: to make systems smarter, faster, and more efficient by connecting everything together. Next comes the IoT hardware layer. At the core of any IoT system is the hardware. This is where data collection begins. We use microcontrollers such as PIC, Arduino, or ESP8266 to interface with different sensors and actuators. Sensors like LDRs detect light, temperature sensors monitor environmental changes, and actuators like LEDs or motors perform physical actions. In the Emertxe Internship, we simulate this hardware using PixSim Lab, which allows us to test real time behavior without physical components. For example, when the LDR sensor detects low light, the microcontroller automatically turns on an LED, representing a smart lighting system. This hardware layer is the foundation that brings IoT devices to life. IoT communication and networking. Once the data is collected by sensors, it needs to be transmitted to other devices or cloud. This is handled by the communication layer. IoT devices use several protocols for communication. For short range, we use UART, SPI, or I2C to connect sensors and controllers. For internet connectivity, we rely on Wi Fi, Bluetooth, or Ethernet connections. To send sensor data efficiently, IoT systems often use lightweight protocols such as MQTT, which works on a publish subscribe model, or HTTP for request based communication. In our project, the microcontroller sends data through these protocols to the cloud or mobile dashboard for monitoring. Reliable communication ensures our IoT system stays responsive and real time. IoT cloud and data handling. The next important layer is the cloud. Cloud platforms store, analyze, and visualize the data collected from IoT devices. Popular cloud platforms like Blink, ThingsBoard, or ThingsPeak are used to build dashboards for real time monitoring. In our project, we use Blink Cloud where the LDR data is sent and displayed on a mobile app. We can also send commands back to control the LED remotely from our smartphone. The data is usually sent using REST APIs or through MQTT brokers and displayed in graphical or numeric forms on dashboards. This makes IoT interactive. Users can monitor and control devices from anywhere, anytime. The IoT application layer. This application layer is where the user interacts with the IoT system. This layer provides visualization, control, and automation. For example, in our home automation system, we use a Blink app to control devices remotely. If the light intensity is low, the system automatically turns on the lamp and the app updates the status in real time. We can also manually override the system and turn the light on or off through the mobile interface. This layer often includes rule based automation like setting a threshold or trigger value for the sensor. Beyond home automation, the same principle applies in other areas, for example, monitoring soil moisture, tracking energy consumption in industries, or temperature regulation in smart buildings. This application layer bridges human interaction with intelligent automation. IoT security and reliability is our next concern. As IoT systems are connected to the internet, security becomes very important. Unauthorized access or weak configurations can lead to data breaches or control over critical devices. To prevent this, IoT systems use authentication keys, encryption techniques, and secure protocols like HTTPS or MQTT over SSL. Regular firmware updates and device authentication also helps maintain security. Reliability is another factor, ensuring devices continue to work even when the network issues occur. In our project, we secure practices by using authentication tokens on Blink platform and ensuring safe communication between the device and the cloud. Security and reliability are what makes IoT practical for the real world use. To summarize, IoT integrates hardware, communication, cloud, and application layers to build smart systems that automate and simplify life. Through the Emertxe IoT internship, I learned how these layers come together to create a working project, from sensing light to controlling devices remotely. Our home automation project demonstrates how IoT can make everyday living more intelligent, efficient, and connected. Thank you.
I am Madhunisha. Now I'm going to explain the home automation project. The first part of the project focuses on automatically controlling garden lights based on the availability of sunlight. Here we have used LDR, which acts as the eye of the system. The LDR continuously senses the surrounding light intensity. When there is a bright sunlight, the sensor value is high and the LED, which represents the garden light, dims or turns off. As the environment becomes darker, the LED brightness increases automatically using PWM control. These mechanisms help in energy conservation and it resembles the automatic street light systems used in modern cities. Now, this part of the circuit automates the garden lights using LDR sensor and an LED. You see the LDR sensor on the right side of the circuit. It continuously senses the surrounding intensity. The analog value from the LDR is read by the microcontroller and displayed on the LED screen. When the slider next to the LDR is moved, that is, reducing the light level, the voltage value drops and the LED or golden light turns on gradually to compensate for the darker side. When the slider is moved upward, the LDR value increases and the LED dims or switch off. The second part of the project focuses on temperature monitoring and control. It includes a temperature sensor, a heater, and a cooler. The LM35 sensor reads the surrounding temperature, and this data is displayed on the both character LCD and the gauge weight in the Blink mobile app. This subsystem reads the ambient temperature using the LM35 sensor and display it both locally and remotely. The temperature sensor is connected to the analog pin of A0 of the microcontroller. In the display, you can see the temperature reading shows T equals to 27.34 degrees Celsius. This value is displayed on the LCD in the circuit and also the gauge weight in the Blink IoT mobile app. The app updates the temperature in the real time, keep both displays synchronized. The cooler can be controlled through Blink IoT mobile app using a button weight. When the button is pressed, the cooler turns on. When released, it is turns off. This feature allows remote control of the cooling system just like a smart home AC systems. The cooler is controlled remotely through the Blink app. On the screen, you see the cooler button, weight, on or off switch. So, when you press on, the app sends the signal to the microcontroller through Wi Fi. The cooler in the
circuit immediately starts rotating and the LCD updates the message. When the button is pressed, the fan stops and the LCD shows cooler off. Similarly, for the heater is controlled using another button, wait on the blink app. At logic high, the heater turns on. At the logic low, it turns off. This allows user to manually manage the heating system from anywhere through the internet. The heater is also controlled remotely through a button wait on the blink app. On the screen, you will see a heater button next to the cooler button. When you tap on the heater indicates in the simulation turns on. The LCD shows the updated state like heater on. Tapping off again sends the commands through the IoT link to turn it off. And again, the cooler is turned on to show the temperature difference when cooler is on and heater is off.
Hello, this is Kalpana. I'm here to explain water tank inlet and outlet valve control. The system reads the tank water volume through serial communication, displays the live volume on the CLCD, and manages the tank level by controlling the inlet and outlet valves through serial commands. This ensures both real time display and automatic water level control. So let's see how it works. This slide shows the condition when the inlet valve is turned on. On the left, the serial remote tank window indicates that the inlet valve activator is active and water is being filled into the tank. The current volume reading is shown as 2750 liters. On the right side, the blink interface reflects the same status. The inlet valve button is in the on state, while the outlet valve remains off. The gauge widget displays the live tank volume as 2750 liters, confirming synchronized monitoring between the tank system and the mobile app. This demonstrates the manual inlet control from the app and real time volume update through serial communication. This slide shows the system behavior when the water tank is full. On the left, the serial remote tank software displays the tank at full level with the volume reading at 3000 liters. Since the tank is full, the inlet valve is turned off automatically to prevent overflow. In the middle, the Blink mobile interface shows the same volume value on the gauge widget, confirming remote synchronization with the tank level. Both the inlet and outlet valve buttons are currently in the off state because no filling or draining is needed. On the right, the notification panel records system alerts. It shows that the water tank is full and therefore the inlet valve has to be switched off. The same notification also contains previous alerts related to temperature control. This demonstrates automatic monitoring synchronized display on both PC and mobile app. This slide shows the system response when the water volume drops below 2000 liters. On the left, the serial remote tank software indicates that the tank volume has decreased to around 1970 liters. Since the volume has gone below the threshold limit 2000, the system has to be turned on. That is, the system has to turn on the inlet valve to start refilling the tank. In the center, the blink application reflects the same status. The inlet valve is shown in the on state and the outlet valve is in the off state. Gauge indicates the live water volume as 1970 liters. On the right side, the notification panel logs the system action. It clearly states that the water volume is less than 2000, so that the inlet valve has to be turned on to refill the tank. This demonstrates the automatic refill logic triggered by low water level and synchronized updates on both the PC and mobile app.